From S2, we have learned about there are 5 index laws here, and these index laws can help us to do the simplification involving index notations. And in S2, all the indices that we talk about are positive integers. And strictly speaking, we need A and B to be non-zero, because if A is 0 or B is 0, then these two are meaningless because we have 0 in the denominator. So that's what we have learned about in S2. And in S3, we started to extend the concept of indices, and we can define the meaning of a to the power 0. So we can actually give a meaning to 0 indices. And in order to define what a to the power 0 means, it has to be consistent with the index laws that we have already had. So a to the power 0 can be regarded as a to the power 2 minus 2. And if we want this to be consistent with what we have here, we need to consider a to the power 2 minus 2 to be same as a to the power 2 over a to the power 2. And that's why this value is known to be 1. And that's what we have learned about in S3. And in S3, we can also define the negative indices like s to the power minus 2. And a to the power minus 2 can be regarded as a to the power 0 minus 2. And in order to make use of the index laws, we need to rewrite this as this one, a to the power 0 over a to the power 2. But we already know that a to the power 0 is 1, so this is same as 1 over a to the power 2. So in S3, we can have a definition for the 0 indices. A to the power 0 is equal to 1. And we can also have the definition for negative indices. A to the power minus n is equal to 1 over a to the power n. So that's the two new definitions of indices introduced in S3. And for these two definitions, a should be non-zero, because if a is 0, then these two are meaningless. In S4, we can further extend the concept of indices by defining so-called rational indices like this. We can actually give a meaning to a to the power 1 over 3. And in order to define what it means, we can first of all consider the power 3 of this. And since we need the definition to be consistent with what we have here, this can be regarded as this one according to the third index law. This is a to the power 1/3 times 3. So that's a to the power 1, which is equal to a. And moreover, we have already learned about the third root of a, and we know that the third root of a to the power 3 is also equal to a. So by comparing this, we can define a to the power 1/3 to be the third root of a. And similarly, we can also define what a to the power 2 over 3 means. A to the power 2 over 3 can be treated as a to the power 1/3 to the power of 2. So that this one is the third root of a, and then square. Or we can do it the other way around. This can be treated as a squared to the power 1/3. And therefore, this is the third root of a squared. Moreover, we can also define the meaning of negative rational indices. And we just apply the same trick here. A to the power minus 2 over 3 can be regarded as a to the power 0 minus 2 over 3. So that's a to the power 0 over a to the power 2 over 3. And that's 1 over a to the power 2 over 3. And we already know what a to the power 2 over 3 means. A to the power 2 over 3 is the third root of a squared. So this one can be defined. So in S4, we can extend the concept of indices to include rational indices as well. So this is no longer confined to integers. It can be rational, it can be fractions. So in S4, we define a to the power 1 over n to be the nth root of a, and a to the power m over n to be the nth root of a to the power m, or the nth root of a and then power m. These two are actually the same. And a to the power minus m over n, the negative rational indices, to be 1 over a to the power m over n. So this is the extended definition of indices to be learned in S4. There's one point to be added here. For this definition of rational indices, we require a to be positive. That means a shouldn't be negative, because if a is negative, then the definition is not so clear here. So let's say now if we want to define minus 2 to the power half, this one according to this is the second root, means the square root of root 2. But we already know that this one is not a real number. So that means it cannot be defined if this one is negative. So this is undefined indices. So for rational indices, we usually require a to be positive so that there is no non-real cases like this.